Omega equals the closed interval 0, 1. Actual probability is the uniform, that is, Lebesgue measure, and we define the risk-neutral probability by the integral formula. Risk-neutral probability of the closed interval a, b, equals the integral from a to b of 2 omega d omega, which equals b squared minus a squared, for a and b between 0 and 1. We may use the fact that actual probability of d omega equals d omega to rewrite the equation as risk-neutral probability of the closed interval a, b, equals the integral over the interval a, b, of 2 omega, d actual probability of omega. Because b of 0, 1 is the sigma algebra generated by the closed intervals. That is, begin with the closed intervals and put in all other sets necessary in order to have a sigma algebra. The validity of the formula for all closed intervals implies its validity for all Borel subsets of 0, 1. Risk-neutral probability of b equals the integral over b of 2 omega, d actual probability of omega, for every Borel set b. This is the general change of measure formula, with z of omega equals 2 omega. Risk-neutral probability of b equals the integral over b of z of omega, d actual probability of omega. Note that z of omega equals 2 omega is strictly positive almost surely, since actual probability of the singleton 0 is 0, and the expectation of z under risk-neutral probability equals the integral from 0 to 1 of 2 omega d omega, which is 1. According to the change of measure theorem, for every non-negative random variable x of omega, we have the equation expectation under risk-neutral probability of x equals expectation under actual probability of x times z, which expands to the integral equation. The integral from 0 to 1 of x of omega, d risk-neutral probability of omega, equals the integral from 0 to 1 of x of omega times 2 omega d omega. This suggests the notation d risk-neutral probability of omega equals 2 omega d omega equals 2 omega d actual probability of omega. In general, when actual probability, risk-neutral probability, and z are related as in Theorem 1.6.1, we may rewrite the two expectation equations. Expectation under risk-neutral probability of x equals expectation under actual probability of xz, and expectation under actual probability of y equals expectation under risk-neutral probability of y over z. As the integral equations, the integral of xd risk-neutral probability equals the integral of xcd actual probability, and the integral of yd actual probability equals the integral of y over zd risk-neutral probability. A good way to remember these equations is to formally write z of omega equals the derivative of risk-neutral probability with respect to actual probability. Equation 1.6.6 is a special case of this notation that captures the idea behind d risk-neutral probability equals 2 omega d actual probability. The nonsensical equation that z is somehow a quote-unquote ratio of probabilities. In example 1.6.4, z of omega equals 2 omega is in fact a ratio of densities.